Hi, welcome to BC Video 10.2a. We're now in Chapter 10. The only section we did in Chapter 7 was 7.4, and we're done. So, Chapter 10, we're going to be looking this time at parametric equations. So you can remember you saw that in pre-algebra. Chapter 10 does start with a section on conics, which we will not be doing. It includes parametric equations and the calculus thereof, and also polar equations and the calculus thereof. So we're going to start with parametric, plane curves and parametric equations. So what you have is a set of parametric equations where basically what's happening is you're expressing x and y in terms of a third variable called t, which is the parameter, which is a set of parametric equations. Now the thing about parametric equations is they have directions, which as t, which is usually time, is increasing, what direction is the particle traveling along that curve in. So to graph it, one method is obviously make a table. You'll be plugging in various values for t, finding the x values that go with them and the y values that go with them, and giving you ordered pairs. So you would end up with this curve right here where I'm just plotting the points. It turns out to be a sideways parabola. But the thing you want to notice is that at t equals -1, you're here. At t equals 0, you're here. At t equals 1, you're here. And at t equals 2, you're here. So as time is increasing, you're traveling along the curve in that direction. The other way of graphing a set of parametric equations is to rewrite it in rectangular form. And the way to do that is to eliminate the parameter t so that you have it in just x's and y's. So, for example, here, forget that for now. If I take this equation, it'll be easy to isolate t. And then I go back to this equation, and I replace the t by y minus 5. And as you can see, sure enough, that would be a sideways parabola. Now, one of the things you need to understand is that since x is equal to t squared, automatically x has got to be bigger than or equal to 0 since it's equal to a square. The direction, it'll ask you to indicate the direction. Again, all you really need is 2 points. As t goes from 0 to t equals 1, you're going from the point 0.5 to the point 1.6. As you can tell from right here, you'll be able to figure that out. And therefore, it's going from this point to that point, so it's traveling in this direction, kind of a a clockwise direction. Okay, on the calculator. So the first thing you'll need to do is go to the graph screen, press menu, select option 3, which is graph entry edit, and select the third option, which is parametric. This is what will show up. So here's your x of t, your y of t. It'll automatically assume, for some reason, that t is between 0 and 2 pi, and that's because traditionally in the old days everything was done with trig, and so they assume you're using sine and cosine, so 0 to 2 pi would be the period. It's also going to automatically have a t-step of 0.13, which basically is pi divided by 24. You want that t-step to be tiny, or you're going to get a very choppy graph, so keep it tiny or don't touch it at all. But these, if there is no trig, okay, unless you're dealing with trig functions, which is fine, but it will be a problem if you're not dealing with trig functions, because why would you want t to only go from 0 to 6? So you would change your t, for example, from -10 to 10, or 0 to 500, or whatever. So here's an example. So you would access the parametric graphing entry screen. You would enter it exactly as you see it. Notice it has to be in terms of t. And if once I press enter, this is what I'll see. And I get to only the top half of this parabola. Now there's a reason I only get the top half of the parabola. And I don't know why. Here it is. Oh, I should be getting both two sides of that parabola. I think you can see that I'm getting it here. I think this just kind of blotted it out somehow. But you do get the two sides of this parabola. Okay? All right. If I was to take this, for example, set of parametric equations and eliminate the t, well, t squared is x, so I can replace t squared by x. Now, The graph of y equals x plus 1 would be this entire line, but this entire line is not the graph of this set of parametric equations. You've got to check. You've got to go back to the original and realize that since x is equal to the square of t, x will be greater than or equal to 0. Since y is equal to the square of t plus 1, the smallest thing this could be would be 0. So the smallest thing y could be would be 1. So you will start at the point 0, 1 and only go to the right of 0 and above 1. In other words, it's only that portion of the line. The other thing we won't do in parametric is we won't put arrows at both ends, because that would confuse the reader as to what the direction is. And if I wanted the direction, if I went from t equals 0 to t equals 1, I go from the point 0, 1 to the point 1, 2, so it is traveling in that direction. Okay, so be careful you don't just eliminate t, get a function and graph it and keep the whole thing. You might get to keep the whole thing, you might not. Okay, so you can eliminate the parameter to get a rectangular equation, or you could make a table, but you've got to check the restrictions on x and y in the original set of parametric equations. The orientation of the curve is based on increasing values of t. Put one arrow only mid-graph, unless there's two branches. Now, when we're dealing with trig, of course, the beauty is to eliminate the t is that you know there's a relationship between sine and cosine, which is that sine squared plus cos squared is equal to 1. And the same thing would be true with tan. Tan squared plus 1 is secant squared, so secant squared minus tan squared is 1. But we have sine and cosine, so I am purposely going to square both sides of each equation and then add them so that I have sine squared t plus cos squared t is 1, x squared plus y squared is 1. Now we know that is a circle. X is equal to sine t. Well, sine t is always going to be between negative 1 and 1. That just naturally happens. Same thing with cos t is always between negative 1 and 1. So y is between negative 1 and 1. But as far as orientation would go, let t equal 0, then let t equal pi over 2. Make sure they're pretty close together. Don't go from 0 to 2 pi, because you'll have the same point. You'll notice we go from the point 0, 1 when t equals 0 to the point 1, 0 when t equals pi over 2. So this is a clockwise. Another example would be x equal tan squared y, y equals secant squared y. Well, we know that if we have secant squared minus tan squared, we have 1. So I'll leave this as plus secant squared. I'll subtract the top equation from the bottom equation, and therefore I will get negative x plus y, and then I get negative tan squared plus secant squared, which is 1. So that's x minus y equals 1, which is y equals x plus 1, which is this graph, but of course, keep in mind that as x was equal to a square, so it has to be greater than or equal to 0, and y was equal to a square as well, and it was the square of secant, which would be greater than or equal to 1. So you start at the point 0, 1, and then you could do the chart here to see that the graph has this direction or orientation. Okay, in 59 through 66, use the graphing utility, so it's with your TI to graph the curve represented by the parametric equations, indicate the direction of the curve, identify any points at which the curve is not smooth. You're really not going to need to worry about that. In other words, where there's sharp turns, that's not going to come up on the BC. So they have all of these equations, and they're very nice. They're letting you know that they have certain names. So we're going to look at 66, which is the folium of Descartes. So it's this set of parametric equations. And if you did it on your calculator, you would see that you get kind of this one petal. So keep in mind, there's no trig functions in here, so do not leave it as 0 to 8, and that's the reason you only get one petal. If you let your T-min go from negative 10 and your T-max be 10, then you'll see the entire graph. Now, there actually is no line here. It's actually a slant asymptote, and you can actually trace the graph to see the direction of the graph.